Okay, welcome to the first meeting this semester of the New England Dynamics and Number Theory seminar. Very glad to see everybody. Today we have Sam Chow talking about smooth discrepancy and Littlewood's conjecture. Go on, Sam.
Great. So yeah, thanks, Dimitri, and thanks everyone for coming along. I'm going to talk about a new bridge between Littlewood's conjecture and discrepancy theory. This is joint work with Nicholas Technow, who's in Bonn. Let me start with the one-dimensional setting. So there we have the corollary to Dirichlet's approximation theorem. It says that if we have any real number alpha, we can approximate it by rational numbers a over n, distance at most 1 over n squared away from alpha. And we can write this succinctly, as I have done here, n times the distance to, from n alpha to the nearest integer is less than 1 infinitely often. Now, this is proved just using the pigeonhole principle, but it turns out that this is already essentially sharp. So there are numbers where you can't replace the 1 here by an arbitrary constant. And these are called badly approximable numbers. And the main thing I want to say is that they exist. This is the best rate that you can get for all alpha. So yeah, examples are root 2 and root 3. They form a full set of full Hausdorff dimension 1. You can characterize them in terms of the continued fraction coefficients being bounded in many nice properties. But the main thing I want to say is that they exist. So this is the best. The corollary to Dirichlet is essentially the best you can do when you're approximating one number by rationals. So when we go to higher dimensions, there are a couple of things you could do. You could take 2 numbers and approximate them by the same denominator and take the biggest error. It's called simultaneous approximation. There's another version of this problem where we multiply the errors. This is called multiplicative approximation. There, the analog of a badly approximable number looks like this. It's a bit harder because n beta is distance from n beta to the nearest integer is at most half. So it's believed that actually there are no such pairs, multiplicatively badly approximable pairs. So this is a famous conjecture of Littlewood that if you approximate 2 numbers at once with the same denominator and multiply the errors, then you can actually beat what you get from applying Dirichlet to one of them. That you can actually beat this naive strategy by an arbitrary constant. So this is a famous problem in diophantine approximation. It's been almost a century and we haven't solved it. And it's also a famous problem in dynamical systems, and we'll touch upon it later. All right, so many people in the field believe that this is true, that Littlewood's conjecture should be true, and you can, in fact, a lot of people believe that you can even strengthen it, so that this is even true with almost an extra log to spare. So this was studied in some papers by Badziahin and Villani and Pollington, and so Badziahin and Villani defined it's mad lambda, where you're badly approximable with this log to the lambda factor. So they conjectured that mad lambda is empty if lambda is less than 1. So this is a strong form of Littlewood's conjecture. If mad lambda is empty, that means that you can always approximate with rate n times log n to the lambda which is a strong form of Littlewood's conjecture if lambda is positive. You can sort of study when when lambda's bigger. You can study mad lambda using generalized Cantor sets. So this result is by Badziahan. So got this result that says that you can't beat Littlewood by a log times a log, which is roughly saying that mad lambda is non-empty for lambda bigger than 1, and actually showed that it has full Hausdorff dimension, 2. But the main thing I want to say is that it's non-empty. So there are pairs alpha and beta where you can't beat Littlewood by a log times a log. Badziahan, yes, suggests in conversation that you can probably get rid of that log. So mad lambda would probably be also full Hausdorff dimension for lambda equals to 1, but this is this remains unsolved. Okay. So that's a bit about Littlewood's conjecture and quantifying Littlewood's conjecture. Before we get into the nitty-gritty, let me talk about the general philosophy that I want to convey in this talk. So if we look at the inequality for Littlewood's conjecture, it looks like this. We take some small epsilon and we want to solve this inequality. And what this is saying is that n alpha n beta lies in a small rectangle modulo 1. Right, so we can look at this sequence n alpha mod 1 and beta mod 1. This is called a Kronecker sequence when you take a vector and take multiples of it and reduce mod 1. And so we're asking about the distribution. Littlewood's asking about the distribution of these points near the origin, and this local to global philosophy that's expressed in some work of Beck, which we'll get to soon, which is as follows: the distribution of points in the Kronecker sequence near the origin determines the distribution throughout the torus on 1z squared, and vice versa. Right, so there should be this local to global principle between the distribution locally near the origin and globally throughout the torus. Right, so we're going to see how that works. But the main thrust of it is that Beck was only able to prove this for almost all vectors, whereas we're going to prove something like this for all vectors, which is what you need to do to prove Littlewood's conjecture. All right, so I've spoken a bit about diophantine approximation. Now I want to talk a bit about the global picture. So we want to talk about how points in a sequence are distributed, points modulo 1. In some torus, points in some torus are distributed. And we measure how evenly distributed they are using discrepancy. So if you consider some points in 0, 1 to the d, I think if you have a sequence, you can cut it off at the first n points, and the discrepancy For the discrepancy, you'll take boxes and you'll count how many points are in the box and then subtract the expected number of points. And the biggest difference as you range over all boxes is called the discrepancy. There's another way to normalize this way we divide by n, but we take this definition, take the biggest difference between the count, the actual count, and the expected count. So uniform distribution modulo 1 is when the discrepancy is little o of n. I want to talk about low discrepancy sequences. So very uniformly distributed sequences are the ones which will be most relevant to us. So before we discuss the discrepancy theory of Kronecker sequence, let's talk a bit about the low discrepancy sequences in general. So you can construct low discrepancy sequences, or you can ask, how low could you possibly have discrepancy of a sequence? So Tatiana Ehrenfest showed that the discrepancy of any sequence is unbounded, whether in any number of dimensions, even in one dimension. And this was famously strengthened by Roth. So you may be familiar with Roth's theorem on the approximation of algebraic numbers. And Roth has another famous theorem on about positive density sets of integers containing 3-term arithmetic progressions. And both of these were cited when he won his Fields Medal, but his favorite paper, his favorite result of his was this one. He used an L2 method and birthed the field of geometric discrepancy theory. The result was sharp for L2 discrepancy, but not sharp for discrepancy as I've described it, infinity discrepancy. And over half a century later, Billig, Lacey, and Vagashakian were able to improve this exponent d over 2 very slightly. And there's still a gap here, so it's not known what the optimal exponent is. We know that it's somewhere more than d over 2 and somewhere less than or equal to d.
Wait, but infinitely often, when you say infinitely often, all of them become variables. Right?
When I say infinitely often, I mean that there are infinitely many positive integers n.
Oh, I see. So they're deterministic sequences.
Yes.
Okay.
For any sequence,
for any sequence.
yeah, there are infinitely many n's, positive integers.
And is this eta explicitly described? What is eta 1?
Eta is explicit. In the case 1, I think, was already understood, wasn't it, by Schmidt, where log n is the answer. D equals 2 is the one that's most relevant to Littlewood, and I think eta is a small number, but I can't remember what. But it's it's certainly less than they give us certainly much less than half in the case d equals 2, and there's some disagreement perhaps on what the right threshold should be. Some believe that the sequences we've constructed should be the best, and d should be the answer. There's a competing view that the right exponent should be d plus 1 over 2. Incidentally, there are a couple of equivalent ways to think about this problem. So the number of dimensions of the problem is d physical dimensions, but there's a hidden dimension for time. and the dimension of the problem actually shifts by 1, whether depending on whether you're talking about sequences or whether you're talking about just point sets. But anyway, this is how we're thinking about it in terms of sequences. Right. So the sequences that we look at are just Kronecker sequences. But it's actually a very interesting problem to think about low discrepancy sequences in general, described in the book of Beck and Chen as the great open problem, and indeed seems to be a difficult one. And there are also open problems about LP discrepancy for different norms P. All right, so somehow we want to relate the discrepancy of a sequence to the multiplicative approximation rate. But I thought I'd start with the case D equals 1 for simplicity. So in the case D equals 1, you're just approximating one number. And the idea is that a Kronecker sequence should have large discrepancy at infinitely many scales, and if and only if the number is well approximable. Well, if you turn it the other way around, if the number is badly approximable, then the multiples of alpha should be well spaced, modulo 1. I guess many of you will know this either from continued fractions or the geometry of numbers or something. So this should be true for all alpha, but the precise connection is only given for almost all alpha, and won't be the one that holds for almost all alpha won't hold for all alpha. So what this is saying is, so there are 3 parts to this. I guess the way that you would prove this is you'd say, well, there's a generic approximation rate, and there's a generic discrepancy bound, and so the first and the third statement are equivalent by Khinchin's theorem, and the second and third statements are equivalent by some other stuff that Khinchin did on continued fractions, and the argument is given in the introduction of Beck's paper, or maybe in the second section. But what I want to get across is the equivalence of the first 2 statements, so that the low discrepancy corresponds to bad approximability with some rate. And as I said, this only holds for almost all alpha, because there's this connection between the rate of this diophantine condition, the rate of bad approximability, and the discrepancy upper bound, and this is tight. Okay, so this was this was already done a century ago by Khinchin. Of course, the problem is more complicated when you pass to higher dimensions. So then in higher dimensions, Beck had this is his main theorem. You have the generic discrepancy bound for a Kronecker sequence. Okay, so so I guess I haven't written this in as informative a way as the previous one. We'll try to clarify this also in this part of the slide and in the next slide. So yeah, there's a generic discrepancy bound, and there's the generic So Beck's result, which was for almost all vectors alpha, the threshold comes from the generic dual multiplicative approximation rate. So simultaneous approximation is about approximating numbers with the same denominator, and dual approximation is about approximating vectors by hyperplanes, or you have some linear form. And the multiplicative aspect here is that we have a multiplicative height. So defined h as the multiplicative height, perhaps unconventionally, as essentially the product of non-zero ni's. Oh, sorry, there is a typo there. I meant to take the absolute value of ni. The product of the maximum of 1 and the absolute value of ni as the multiplicative height of them. And when I say infinitely often there, I mean for infinitely many integer vectors. And right, so at this point it looks a bit ugly. There's this generic discrepancy bound for the Kronecker sequence, and there's this generic dual approximation rate. Maybe the connection between them is a bit messy. There it is precise, and yeah, so on the next slide, I'll give a sort of simplified version of this, which is sort of really what's going on and what would go on if we made a simplifying assumption about f. So before we move on, let's just recap that Beck's local to global principle gives a relationship between dual multiplicative approximation and discrepancy that's tight, but it only holds for almost all alpha. All right, so now let me give a sort of cartoon version. So the phi that we're interested in are pretty low, pretty slow growing, like logs or log powers. If we're interested in proving Littlewood's conjecture or thinking about low discrepancy sequences, and if you input that and you unpack it a bit, this is what Beck shows. That if you have multiplicative bad approximability with this extra phi, then this is equivalent to the discrepancy being big O of phi of n for almost all alpha. So we'll talk a bit about so I will say what the true right answer is that holds even for more general phi. But this is for the phi that we're interested in. This is the right answer. The right answer, except that it will fail for some alpha. So in the case d equals 1 and 2, it fails, for instance, for some alpha, even if phi is very nice and slow growing. So when d equals 1, you can, if alpha is badly approximable, you can take phi bounded in the left-hand bit and get a sequence of bounded discrepancy if it were true. And this is, of course, false. Know that sequences have unbounded discrepancy. And when d equals 2, it's also impossible for this to be true for all alpha. Because there's a dual analogue of Bad-Ziahen's theorem, which he actually needs to prove both the dual multiplicative and multiplicative parts at once in order to get in order to get the main result. So the dual analogue of Bad-Ziahen's theorem is what I wrote down here in the display equation. There alpha where where you can't beat Littlewood in a dual multiplicative sense by log times log log. And again, you get an impossibly small discrepancy by the Billig-Lacey-Vagashkian result that you get at least log to the 1 plus eta infinitely often. So it's actually, I was initially skeptical about this project because what we're trying to prove is false. But thankfully we continued. And we were able to prove a deterministic version, but we needed to change the definition of discrepancy to smooth discrepancy. That's what I'll talk about next. All right, so in the definition of discrepancy, we're counting in boxes, and we're counting points in the sequence in boxes, and this uses a sort of sharp cutoff where you either count it completely or not at all. And you can also count with the smooth cutoff into this bump function. And if you smooth in all the space dimensions, then this was done in the paper of Temlyakov's and some other work. And it's actually something that features prominently in numerical integration. It's called quadrature when d equals 1, and it's called cubature when d is at least 2. Well, what we found is that it's also very important for us to smooth in the time dimension. So there's this extra time dimension for the term n of the sequence. So what we want to do is put smooth weights there. And we want to use non-negative weights where the Fourier transform is also non-negative, and we can you can construct such weights. So yeah, the definition is a bit to take in, but we have some box centered at some vector gamma, and with scale parameters rho, so scaled by rho 1 up to rho d, and yeah, so we'll scale up time to scale n, and this omega is just the volume of the box when integrated against the weights, and this is proportional to the Beck volume. And for the smooth discrepancy, so we take our box and we count with these smooth weights. Smoothing also in time, and we subtract the expected count, which is the corresponding integral. And we take the difference and we take the supremum over all boxes. So this we call the smooth discrepancy. Right, so initially one might think, well, you just smooth it. How much difference can it make? When you get to very low discrepancies, it turns out that it makes a difference. We actually see cases of where the smooth discrepancy is smaller than the classical discrepancy of any sequence, and even bounded in dimension 1. So to state our results, I first introduced the precise threshold, which is something we wouldn't have guessed, is given by phi of L of n. So L of n is defined implicitly by L of n times phi of L of n equals n. And we find that the right threshold is phi of L of n. And we sort of had observed, and as I discussed before, that for nice slowly increasing phi that we're interested in, the right threshold should be phi of n, and it is. So it's phi of L of n generally, but this this is phi of n up to a multiplicative constant for nice slowly increasing phi. So I'm going to state it in two parts. One is the discrepancy upper bound that comes from dual multiplicative diophantine assumption, but this is tight, so I'll give the complementary lower bound on the next slide. So for this upper bound, we did need a doubling assumption on phi, and for the corresponding lower bound.
Sam, in the conclusion of your statement, what is the role of omega? So it's absorbed in the implicit constant, is it?
Yes.
So it's true for any omega, and the conclusion is true up to an implicit constant depending on omega.
That's right.
So the statement is true for any omega, any weight, and the conclusion is says that the implicit constant depends on omega and nothing else.
Yeah, well, I mean, it will depend on the dimension.
Yeah, sure. I mean, okay.
You could say that's part of what omega is, but yeah.
Okay, fair enough. Yeah.
Yeah.
Thanks.
So this is sharp. So this is like the bad approximable dual multiplicative sense, gives low discrepancy, and we also have a result which says that well approximable in a dual multiplicative sense gives larger discrepancies infinitely often, and the threshold will match this one. So this is what I've stated here. So yeah, it's the same in threshold to a multiplicative constant, and we don't need the doubling assumption for the lower bound. Okay, so I've hyped up the Littlewood conjecture part quite a lot. So maybe we should talk about that. I think I have that here. Yeah. So let's start with Littlewood's conjecture. Is the d equals 2 case of what's written here. And when you increase to higher dimensions, if you have d bigger than 2, then the problem should become easier. So you're multiplying by things that are at most half, but they're also very much open. And there's a dual form of Littlewood's conjecture, so this is why we can get away with using dual multiplicative approximation. Talk about Littlewood's conjecture. Because the dual form of Littlewood's conjecture is equivalent, known to be equivalent to Littlewood's conjecture. So there's a known formulations of Littlewood's conjecture, and we present another one that's equivalent. So we conjecture that if d is at least 2, then any d-dimensional Kronecker sequence is unbounded smooth discrepancy. Yeah. So I've said everything with bump functions. Actually, for this particular, you can quantify how much smoothness you need, and C3 is enough. C3 smoothness is enough. 3 continuous derivatives are enough for this statement. Yeah, the essence of it is that we conjecture that any two-dimensional Kronecker sequence has unbounded smooth discrepancy if d is at least 2, and we prove that this is equivalent to Littlewood's conjecture. Well, that follows from the theorems that I wrote on the previous 2 slides. So we know that any sequence has unbounded classical discrepancy, no matter how many dimensions we're working in. So it's pretty plausible that any sequence should have unbounded smooth discrepancy as well. But we haven't been able to prove that. So we go via the Downey correspondence. Don't use dynamics, but we use the Downey lattice and the dual Downey lattice especially, and I guess it's because good multiplicative approximations correspond to points in the Downey lattice that are multiplicatively short. The multiplicative height of the first D components times the final component is small. And this is also true on the dual side. So the dual multiplicative approximations correspond to multiplicatively short dual Downey lattice points. So we get results for Downey lattices and dual Downey lattices, and there's also extends. So we get results not just for these, but also for any unimodular lattice. That's the determinant 1. So we get more general results than just for Downey lattices. And so we introduced this lattice discrepancy, which is a distinct but related notion, where it's just the difference between the count and the expected count. So we have smooth weights, the difference between the smooth count and the expected smooth count, and you take the absolute value and take the supreme and biggest difference over boxes B. And so we get the same results. We get the same results in this setting. So a diophantine assumption is just that we don't have any very multiplicatively short lattice points in the dual lattice. And so I also want to mention that Littlewood's conjecture generalizes to Margulis's conjecture, and we think we have a generalization of a special case of Margulis's conjecture we expect to be true. So there's this Castles and Swinnerton Dyer version of Littlewood's conjecture, which is a bit more general. If you have a product of 3 linear forms, and they're not proportional to an integer polynomial, then you have then they take small values at integer vectors, and there's sort of some obstructions that crop up when you they come from norm forms. So you can take some linear forms with irrational coefficients, but you multiply them and you get something. You get integer coefficients. You can construct these examples from norm forms which come from algebraic number fields. So that sort of motivates this, and this is equivalent to a special case of Margulis's conjecture. I believe people consider to be probably true. And this is about diagonal orbits in the homogeneous space S3R mod S3Z. So here we're seeing a bit of the connection to homogeneous dynamics without explaining anything. And what we think is true is this. So yeah, this is quite complicated, but you consider the rows of the matrix corresponding to the dual lattice, and you assume that the product of linear forms from that is not rational, and the conclusion is that you have unbounded smooth discrepancy. Yeah, so this is very well, if you unpack this and apply our theorems, then this is very similar to Castles and Smith and Dyer, what you get, except that the height is not exactly a product of the terms. You take the maximum of the absolute maximum of 1 of the absolute values. So sometimes you'll get 1 instead of some small number. And this conjecture implies the Cassel-Swinners and Dyer conjecture, and hence that special case of Margulis's conjecture. All right, so yeah, so let me finish by talking a bit about the methods. So there's sort of two parts to the argument of the upper bound. So so one thing that we want to use is the geometry of numbers. So you have lattice translates and want to intersect them with convex bodies or just this axis parallel boxes. So we think about these as Bohr says, because they, in the case of the Dani lattice, we get the we essentially get the lifted Bohr sets that we used in some previous work on Littlewood, and but these are very general objects. They're just lattices intersected with boxes, and we want to bound the cardinality of these, how many lattice points there are in these boxes. And there's a base point trick where we can assume that gamma equals 0 by sort of shifting by a putative element of the set. And then if we want to, if we have some symmetric convex body, we can apply Blichfeld's theorem to say that, well, if you have a full linearly independent set of vectors in your region, then the number of lattice points is big O of the volume. Well, if the determinant is 1, as it is. And so we want, so this is the same as saying that the kth successive minimum of the lattice with respect to the body is the most 1. And there's an inverse relationship between that and the first successive minimum of the dual lattice with respect to the dual body. So we want to show that the first successive minimum of the dual lattice with respect to the dual body is bounded away from 0. And this is to say that there are no short vectors. There are no short lattice points, short dual lattice points in the dual body, and that comes directly from the diophantine condition, as long as the box is multiplicatively large enough, it's large enough volume, And the threshold that comes out is decomposed with L. And we call it the Bohr threshold because that's how we think about it. So maybe you might guess that this is what we do for large boxes B. So you have to bound the discrepancy for large boxes B and for small boxes B. But paradoxically, it's the other way around. So it turns out that if we have large boxes B and we apply this, then we're not getting an error term. We're just getting a multiple of what we expect to get, and it's not precise enough. We actually use this for small boxes. So if you have a smaller box, then these volumes are within, they're smaller than or bigger of our target. Yeah, smaller than our target. And you just want to make sure that the count is not too large. And we do this by inflating the boxes to reach the Bohr threshold and then applying the estimate. And we get what we want. And the smoothing plays no role here. We just majorize the smooth count by a sharp count, by an indicator function count. And we get the cardinalities of these Bohr sets out. And the real action is happening on the Fourier side for large boxes when we try to get something more precise. That's where the smoothing kicks in. So for larger boxes, we apply Poisson summation. So the lattice discrepancy will be minus the expected thing plus some smooth function over lattice points. So I'm just writing, okay, this end. So there's a sort of large final scale. You've got small initial scales relative, and gamma k is 0, and then we get this expression. And then we can apply Poisson summation, so it's the sum of the function. The lattice points will be some Fourier transform at dual lattice points. So this is what we get, and the zero frequency will cancel this this volume term, and so the discrepancy will be some non-zero vectors. And the idea is that if we were just trying to estimate this thing, there should be a contribution from the good approximations, and then the Fourier decay of bump functions will give us, will tell us that that's really the main contribution. Comes from very good approximations. So what we do is we show that we have a gap principle. So we want to know these terms. So we sort of zoom in on the final term. So we have Fourier decay at some polynomial rate, and yeah, we can quantify how much smoothness or how many continuous derivatives we need. But we have Fourier decay and this final thing. So this final let's see, yeah, this final thing omega k hat of n lambda k establish a gap principle for n lambda k. And lambda k is the projection of the lattice point onto the final coordinate. I'm going to do a lattice point onto the final coordinate, and the diophantine condition tells us that that first of all it can't be too small, and also that there are gaps between these. So you combine this with Fourier decay doubling assumption, and we get what we want. So there's the upper bound, the small box regime we hit with no room to spare. The large box regime we also hit with no room to spare, and the lower bound we also now hit with no room to spare. So so we could get a lot of intuition actually from this lower bound. Believe that they would that we would make ends meet and make everything sharp. So we choose gamma equals 0, and then all of those twists that come from the Fourier transform go away, and we just have these non-negative terms. And all we need to do is realize a large contribution, single large sum, and we get this from a good approximation if we choose all of our scales. And again we get this v of L of n. Basically, because this h of lambda will have to be at least L of n here, and by choosing c to be a small constant, we get a contribution from the summand, which is bounded away from 0 and then multiplied by the volume term. All right, so that's all I have to say. So thanks very much for your attention.
Okay, let's give a virtual round of applause for Sam. Any questions? No. So just just to reiterate the main statement, what you proved is that the statement of Littlewood's conjecture is equivalent to this discrepancy being unbounded, and this
Yes.
so I understand that it doesn't prove or disprove the conjecture, but can it be used to construct either examples of explicit alpha satisfying the statement, or maybe
So
there's also an industry of proving that some specific pairs, for example, satisfy Littlewood's conjecture.
Right.
Which is not easy to prove.
Specific pairs satisfy Littlewood's conjecture. Oh, okay, so you're asking if for some specific pair we can show that we have unbounded smooth discrepancy, or disprove that. Yeah.
Well, this proof will be great.
Or yeah. Yeah, I don't know. I don't know about that. Yeah, we don't know how to do that. So we do know from everything that we get. We can get examples of bounded smooth discrepancy in one dimension, and smaller smooth discrepancy than the classical discrepancy of any sequence in 2 dimensions. But yeah, I don't know if we can construct new or find new pairs alpha and beta such that Littlewood holds using this. Yeah, it's an interesting thought, but yeah, I don't know how to do that.
Okay.
To follow up on Dimitri's question, can you prove an analog of the Erdős-Turan inequality for smooth discrepancy?
Oh.
That's precisely what gives you an estimate on the discrepancy of a sequence.
I don't know, around this smooth discrepancy. I mean, I think that I think so.
Can I give a comment? I
Yes.
think that Sam's proof is stronger than Erdős-Turan inequality because it looks like to be related to famous Skriganov argument, isn't it?
Somehow it should be better because we have
It should be
all this
better.
moving and stuff. Yeah, it should be better.
Erdős-Turan loses one logarithm in ordinary situation, and
True,
this
but-
post-summation doesn't lose anything.
True, but that's because Erdős-Turan is for the upper bound and the discrepancy. If you look at the lower bound, it's Koczma-Klawka, which is known to be short, if I'm not mistaken. So it depends on what you want to prove, but if you want to prove unboundedness, then Koczma-Klawka gives you sharp lower bounds for the discrepancy. And so the question is whether there is such an analog in the smooth case.
So yeah. So if you want to show the unboundedness of classical discrepancy of all sequences, I guess there's Roth's argument and versions of Roth's argument. You're saying that the Koczma-Klawka inequality can also prove that, or?
It gives you a lower bound which is either known or expected known to be sharp for the discrepancy. So if you want to prove unboundedness, there would be one way. I mean, surely that your method also works, but that gives you another way to approach the problem.
Okay.
And you need a smooth version of that, of course.
Right. Okay, yeah, we'll check it out.
Anyway, thanks for the nice talk. That was lovely, as usual.
Cheers.
Any other quick questions?
Yeah, a short question. Discrepancy is invariant when you shift it so translate it. Does this also naively, I would guess, like this gives you also something on Littlewood's conjecture in the inhomogeneous case, or is this too simple, what I thought here?
Oh, inhomogeneous Littlewood conjecture. Wouldn't have thought so, because, well, inhomogeneous Littlewood, you need to make an assumption, right?
Yeah, exactly. But where do you see the assumption? That's somehow what puzzles me here.
we do a bit on the dual side, so
Okay.
it takes a bit of unpacking.
But the approximation is not translating alpha; it is translating alpha after multiplying by n. So it's
yeah, that's right. Yeah.
So it's a bit trickier than just translation.
Okay.
Yeah.
Okay, if there are no short questions, let's thank Sam for a great talk. Another round of applause. And thank you all for coming, and we'll meet again, hopefully soon.